Good day everyone, welcome to this course on circuit analysis. Module 1, the basic circuits, network topology, and network theorems. 1. Introduction to circuit analysis. Welcome everyone. Today we begin our deep journey into circuit analysis, one of the cornerstones of electrical and electronic engineering. Think of this field as the language that allows us to understand, predict, and control how electricity behaves in any electrical system, from the simplest flashlight to complex power grids and communication systems. Circuit analysis gives us the tools to describe the relationships between voltages, currents, and the components that make up a network. Whether these components are resistors, capacitors, inductors, or sources of energy, the same principles apply. It's the application and combination that changes. We are going to start with the fundamentals, because without them, all the advanced methods you learn later will feel like memorizing magic tricks instead of understanding a science. 2. Ohm's law. Let's begin with Ohm's law, probably the most famous equation in electrical engineering. It tells us that the potential difference across a conductor is proportional to the current flowing through it, provided the temperature remains constant. In plain language, if you push harder, increase voltage, more current flows. If the material resists more, less current flows. Even without giving you the formula, you should remember this relationship as a balance between voltage, current, and resistance. This principle applies to many materials we call ohmic, things like metals where resistance stays constant under stable conditions. Of course, some materials don't obey Ohm's law strictly. We call them non-ohmic, like diodes or filament lamps where the resistance changes with temperature or voltage. 3. Kirchhoff's laws. Moving on, let's talk about Kirchhoff's laws, the bread and butter of circuit analysis. There are two of them. Kirchhoff's current law, KCL, which says that the total current entering a junction equals the total current leaving it. This is simply the conservation of charge in action. Kirchhoff's voltage law, KVL, which says that if you travel around any closed loop in a circuit, the sum of all voltage rises and drops will be zero. This is conservation of energy in electrical form. With these two laws, you can analyze practically any circuit, no matter how complex. 4. Mesh current and node voltage methods. Now that we know the fundamental rules, we can start applying them in systematic ways. Mesh current method. This method involves defining a mesh current that flows in loops within the circuit. You then apply KVL to each loop to get equations for the mesh currents. Once you solve for them, you can find the actual branch currents. Node voltage method. This focuses on points, or the nodes, in the circuit. We assign a voltage variable to each node and apply KCL, writing equations in terms of those node voltages. This method is especially efficient when there are more nodes than loops. Both methods are just clever ways of applying Kirchhoff's laws to keep the algebra manageable. 5. Network terminology. Before we go deeper, we need a shared vocabulary for circuit diagrams. Some key terms. Branch, any path connecting two points, containing an element like a resistor or capacitor. Node, a junction where two or more branches meet. Loop, any closed path through the network. Mesh, a loop that contains no other loop within it. Understanding this helps you interpret and model circuits systematically. 6. Graph of a network. A circuit can be represented as a graph, a mathematical abstraction made of vertices, nodes, and edges, branches. This allows us to apply graph theory to electrical networks. The advantage. Complex networks can be studied without thinking about their physical layout, only their connectivity. 7. Incidence and reduced incidence matrices. An incidence matrix records the connection between nodes and branches in a network, assigning values that indicate the direction of current relative to the nodes. A reduced incidence matrix simply removes the row corresponding to the reference node, ground, which is useful when solving equations for the other node voltages. 8. Trees, cut sets, and tie sets. A tree in network theory is a set of branches that connect all the nodes without forming any closed loop. Cut sets are formed when certain branches are removed from a network, breaking it into two separate parts. The fundamental cut sets are linked to a chosen tree and correspond to independent current equations. Tie sets are groups of branches that form closed loops when combined with branches of the tree. These concepts help us systematically set up equations for large networks. 9. Link currents, twig voltages, and schedules. In tree terminology, twigs are the branches of the tree. Links are the branches not in the tree. A link current is the current through a link branch, while a twig voltage is the potential difference across a twig. A tie-set schedule is a table relating link currents to branch currents, while a cut-set schedule relates twig voltages to branch voltages. 10. Duality and dual networks. In electrical networks, duality refers to the correspondence between two systems where the roles of certain quantities are swapped, like voltage with current, series with parallel, KVL with KCL. Understanding dual networks gives insight into symmetry in electrical systems and allows for alternative analysis methods. Network theorems for DC and AC circuits. 11. Superposition theorem. In any linear circuit with multiple sources, the total response, current or voltage, at any point is the sum of the responses caused by each source acting alone, with all other sources turned off, voltage sources replaced by short circuits, current sources by open circuits. 12. Thevenin's theorem. This tells us that any linear circuit seen from two terminals can be replaced with a single voltage source in series with a resistance or impedance in AC. It's especially useful for simplifying parts of a network when analyzing load behavior. 13. Norton's theorem. Similar to Thevenin's, but instead of a voltage source and series resistance, we use a current source in parallel with a resistance. Thevenin and Norton are interchangeable through source transformation. 14. Reciprocity theorem. This theorem applies to certain linear, bilateral networks, stating that if a voltage source produces a current in one branch, placing the same voltage source in that branch will produce the same current in the original source location. 15. Millman's theorem. Useful for circuits where multiple branches, each with a voltage source and series resistance, are connected in parallel. It allows us to find the overall voltage by a simplified calculation. 16. Maximum power transfer theorem. This theorem says that a load receives maximum power when its resistance equals the Thevenin resistance of the source network. In AC circuits, the condition is slightly extended to match the magnitude of impedances. 17. Network reduction techniques. Voltage and current division, simple proportional relationships in series and parallel arrangements. Source transformation, converting between equivalent Thevenin and Norton forms. Star delta, Y delta, conversion, allows transformation between three-terminal resistor arrangements, useful when direct series parallel reduction isn't possible.